Good morning, everyone. My name is Jordan Chin Yun Nong, and today I will be presenting on the topic behavior of light in relation to the human eye. Thank you for being here. Let's begin with a simple idea. Light is the foundation of vision. Our eyes are like a natural camera. They collect and focus light to form image. In this presentation, I will explain the basic properties of light, how it travels through the eye, and how this process allows us to see. So what actually is light? Well, light is a bit of voodoo. It has two natures. It acts like a wave sometimes, and like a particle other times. It travels ridiculously fast. We are talking about 300 million meters per second. But when it goes through things like the liquid in our eyes, it slows down and a little bit. The light we can see, what we call the visible spectrum, it's just a tiny part of all the light out there. It's like a rainbow, from purple to red. And here a fun fact. The blue light from your phone has more energy than red light, which is why it can sometimes cause your eye strain. Now, let's talk about path of light through the eye. Let's imagine a beam of light going into your eye. Where does it go? It's like a journey. First, it hits the clear front part, the cornea. Then it goes through a watery liquid called the aqueous humor. Through the black hole in the middle, that's the pupil. Then through the lens, and finally through a jelly-like substance called the vitreous humor, before it finally hits the back of the eye, the retina. Each of these parts has a job to do, make sure the light ends up in the right place. Let's start with the cornea. Think of it as the eye front window and its most powerful lens. This is transparent. Dome-shaped structure is where the light gets its first and biggest band. In fact, it provides about plus 43 diopters of the eye's total focusing power. That means roughly 2/3 of the work needed to focus light happens right here. The reason is physics. When light moves from the air into the denser corneal tissue, it slows down and bends sharply. This is why the cornea shape is so crucial. If it's not perfectly curved, like in astigmatism, the light scatters and vision becomes blurry from the very beginning. Now let's move to the role of the lens, the eye's incredible fine-tuning system. Sitting right behind the pupil, it edits the remaining plus 119 diopters, but its real magic is its flexibility, a process called accommodation. Here a deeper look at how it works. The lens is suspended by tiny jonular fiber connected to the cherry muscle. When you look at something far away, this muscle is relaxed, pulling the lens flat. But the moment you look at something close, like your phone, the brain sends a signal. The cherry muscle contracts, which releases the tension on those fibers, allowing the natural elasticity of the lens to make it become thicker and rounder. This change is increase its optical power, bending the light rays more sharply to project a clear image of the neighboring object onto the retina. It is continuous, automatic, and precise adjustment that gives us seamless vision from far to near. Finally, we have the transparent media that fills the eye, the aqueous and vitreous humor. The aqueous humor is clear watery fluid that fills the space between cornea and the lens. But it's not static, it's constantly flowing, and this circulation is vital. It delivers essential nutrients to the avascular cornea and lens, which lack a blood supply, and it simultaneously carries away their waste product. It also maintains a stable pressure inside the front of the eye, which is critical for maintaining the eye shape. Behind the lens, we find the vitreous humor, This is a stable, gel-like substance that fills the large cavity all the way to the retina. Its gel consistency gives the eyeball structural integrity, helping it maintain its round shape. It also acts as a shock absorber and helps keep the retina gently placed against the back of the eye. Most importantly, for vision, both of these humors are perfectly clear, creating an unobstructed pathway for light to travel from the lens all the way to the retina. Next, we go through the refraction and image formation. This bending of light we have been talking about has a formal name. It's called refraction, and it's not random. It follows a specific physical principle called Snell's law. In simple terms, Snell's law tells us that when the light passes from one material into another, like from air into the cornea or from the aqueous humor into the lens, it will be bent at an angle that depends on the density of those materials. This is actually why a straw looks bent in a glass of water, and it's the same principle the eye uses to focus. The cornea and the lens are perfectly shaped to bend or reflect the incoming light rays according to this law, making them all converge at a single precise point on the retina. Now, here the fascinating consequence of this process. Because of the way the light rays cross over as they are focused, the image projected onto your retina is actually upside down and reversed. But don't worry, your brain is incredible to process. So it instantly flips this image right side up, allowing you to perceive the world correctly. Alright, now we talk about optical phenomena in the eye. Beyond basic refraction, our eye experiences some other fascinating optical phenomena. Let me walk you through three key ones. The first is refraction. This is not just about mirrors. Inside the eye, refraction is actually a useful tool. For example, when an optometrist uses that bright light from an ophthalmoscope or retinoscope, they are seeing light reflected back from your retina. This reflected light helps them see inside your eye and check its health. And the next is dispersion. Remember how white light is made of all the colors of the rainbows? Dispersion is what happens when white light split into these different colors. It's the prism effect. In the eye, this can sometimes cause cosmetic aberration, where different colors focus at slightly different points. It's one reason why you might see subtle color figures around bright objects in certain conditions. Finally, we have the aberrations. These are imperfections in the eye optical system. Spherical aberration happen because the cornea and lens are curved, so light rays hitting the edge bend differently than those hitting the center. Chromatic aberration, as I just mentioned, is due to dispersion. And astigmatism, which many of you might have heard of, is actually another type of aberration caused by an uneven corneal curvature. What's interesting is that despite this phenomena, our visual system has clever ways to minimize their impact, giving us the clear vision and we enjoy most of the time. Now we talk about refractive errors. What happens when this system is not perfect? We get what are called refractive errors, which is just a fancy term for needing glasses. If you are nearsighted or myopic, your eyeball is a bit too long, so light focus in front of the retina, making far away things blurry. If you have farsighted or hyperopic, your eyeball is big too short, so light tries to focus behind the retina, making close-up things blurry. The next, astigmatism, is when the cornea is shaped more like a football than basketball, causing blur at all distance. And as we get older, our lens gets stiffer and can't change shape as well. That's called presbyopia, which is why many people over 40 above need a reading glasses. Now that we understand how light behaves in the eye and what can go wrong, let's talk about the practical side, clinical relevance. This knowledge is not just theoretical, it's the foundation for diagnosing and treating vision problems every day. In practice, this means we have several effective ways to correct refractive errors. The most common are spectacles and contact lenses. Both work on the same simple principle. They add a precisely shaped external lens in front of the eye to bend the light correctly before it even enters the cornea, compensating for the eye's own focusing flaws. For a more permanent solution, we have refractive surgery, like LASIK. This procedure uses a laser to carefully reshape the cornea itself, physically altering the eye's maintain focusing elements to correct its power. These applications are fundamental in both optometry and ophthalmology. Understanding this optical principle allows eye care professionals to accurately diagnose the specific nature of a vision problem and then choose a design the most effective treatment, whether it's prescribing the right pair of glasses or planning a delicate surgical procedure. So in summary, we have seen that light undergoes a complex journey of the refraction and transmission within the eye, from the powerful bend at the cornea to the fine-tuning by the lens, and through the clear media of the humus. Every step is crucial. This process shows us that vision is not the job of single part, but the result of the synergistic interaction between all these ocular structures working in perfect harmony. And this is why understanding these fundamental optical principles is so critical. It's not just academic knowledge, it is directly instrumental. It is the foundation that allows eye care professionals to better diagnose the root cause of vision problems and precisely correct a wide range of visual impairments, ultimately restoring and protecting the precious gift of sight. That's all for my presentation today. Thank you.